Hi! In this lecture, we're going to solve another problem using greedy algorithms, a celebration party problem. So, imagine the following situation. Many children came to a celebration party, and you need to organize them into groups. But you want them to play nicely with each other, so you want the groups to be pretty homogeneous, and for that you wish that any two children in the same group should differ by at most 2 years of age, not more. So you want to organize them in the minimum possible number of groups, because for each group you need an adult to supervise this group, and you want to minimize the number of adults that have to be doing that. So, all in all, the problem is to organize the children into the minimum possible number of groups, such that any two children in the same group differ by at most 2 years of age. And we could try to solve this problem with a naive algorithm. So just try all possible distributions of children into one or more groups and see which one is valid and which one is also with the minimum possible number of groups. So just for each distribution, check whether any two children in any of the groups differ by at most 2 years of age. And if that's true, then consider this distribution valid and then return the minimum number of groups among all the valid distributions in the groups. So this algorithm obviously will work because it will consider all the possible distributions of children to groups, but there is a small problem with this algorithm. It's running time. And the lemma states that the running time of the naive algorithm is at least 2 to the power of n, at least exponential, where n is the number of children. And that is bad. The running time of this algorithm obviously will work because it will consider all the possible distributions of children to groups, but there is a small problem with this algorithm. It's running time. And the lemma states that because it will consider all the possible distributions of children to groups, but there is a small problem with this algorithm. It's running time. And the lemma states that the running time of the naive algorithm is at least 2 to the power of n, at least exponential, where n is the number of children. And that is bad, but we will see in a few. So this algorithm obviously will work because it will consider all the possible distributions of children to groups, but there is a small problem with this algorithm. It's running time. And the lemma states that the running time of the naive algorithm is at least 2 to the power of n, at least exponential, where n is the number of children. And that is bad, but we will see in a few minutes why it is bad. And to prove that this algorithm is at least exponential in complexity, and the lemma states that the running time of the naive algorithm is at least 2 to the power of n, at least exponential, where n is the number of children. And that is bad, but we will see in a few minutes why it is bad. And to prove that this algorithm is at least exponential in complexity, we should notice that this algorithm is going to consider at least all possible distribution of children into exactly 2 groups. It will also consider distributions into one group and more than one group probably, but at least all the distributions into 2 groups it will consider. And if you are going to distribute all n children into 2 groups, then first of these 2 groups corresponds to any subset of children. You can just group any subset of children into the first group and then all the other children in the second group. And there are 2 to the power of n different subsets of the set of n children. So there will be 2 to the power of n different distributions into 2 groups. First group is a subset and second group is all the other children. As our naive algorithm is going to consider all those distributions, and there are 2 to the power of n of them, the running time is at least 2 to the power of n, and actually it is much more than that. So this is not a very good algorithm. So naive algorithm works in time omega of 2 to the power of n, which means that it works in time at least 2 to the power of n. And for n equal to just 50 children, it is at least 2 to the power of 50, which is this huge number of operations. And you're probably not going to wait until your laptop computes the result for this algorithm. You won't be able to wait for that. So we're going to do much better than that. We'll improve this significantly using a greedy algorithm. And we're going to do that right in the next video. And the lemma states that this algorithm Hi, in the previous video we've considered a celebration party problem and we've came up with a naive algorithm, but it turned out to be too slow. And I promised you that we are going to overcome this with a greedy algorithm. But first we're going to consider a seemingly unrelated problem, covering points by segments. So you're given a set of n points on a line with coordinates x1, x2 and up to xn, and you need to find the minimum number of segments with each segment of length at most 2, which are needed to cover all those points. For example, this is the line and a few points are marked on it, and above it there are a few segments which cover all these points, and all the segments have length 2. So every point is under some segment. Another example to cover these points is below the line, so there are just 3 segments to cover all these points. So the solution above is not optimal because there are 4 segments and we can do better. We can do with just 3 segments. And the solution below is actually optimal. We cannot do with less than 3 segments to cover these points. So what is the connection? The connection all these points. So the solution above is not optimal because there are 4 segments and we can do better. We can do with just 3 segments. And the solution below is actually optimal. We cannot do with less than 3 segments to cover these points. So what is the connection? The connection is actually quite simple. If we consider those points and their coordinates x1, x2 and up to xn as age of the corresponding child, then points x1 up to xn correspond to the children's ages, and the segments will correspond to groups. So actually, any 2 children within the same segment, if 2 children correspond to points and those 2 points are within the segment of length 2, then the ages of any 2 children inside the segment differ by at most 2 years of age, because the segment has length 2, so any 2 children inside this segment cannot differ by more than 2. And so any valid group of children, any group in which any 2 children differ by at most 2 years of age, can be put into a segment of length 2, from the minimum age of the child, for example, in this group, to the minimum age plus 2. All other children will get into this segment of length 2. So this is the connection, and it means that to group the children into the minimum possible number of valid groups is equivalent to covering the corresponding points with the minimum possible number of segments of length at most 2. So now we're going to solve the problem about points and segments instead of the celebration party problem itself. And we're going to solve it with a greedy algorithm using the following greedy choice. So we are going to cover the leftmost point with a segment of length 2, which starts with this point, so that the left end of the segment is in the leftmost point. And we're going to prove that this is actually a safe choice, so that we can use it in our greedy algorithm and it will work correctly. To prove that, we need to show that there is an optimal solution which is consistent with this safe choice. To prove that, consider some optimal solution. So assume that the solution below with the points and the segments is optimal, and the minimum number of segments of length at most 2 to cover these points is 4 in this case. And consider the leftmost point, marked with green now, and consider the segment that covers it. This is a solution, so there is some segment that covers it, it's right above it, and it's in red. So if this segment doesn't start in this point, if its left end is not the same as the leftmost point, then we can just move this segment to the right until its left end coincides with the leftmost point. And while we're moving this segment to the right, we don't lose any of the points because the green point is the leftmost point. So while we're moving, there are no points below the left end of the segment. And when we move this segment to the position where its left end is directly above the leftmost point, we have an optimal solution with the same number of segments, so it is still optimal. All the points are still covered, so it is still a solution. And in this solution, the first segment has the left end coinciding with the leftmost point. So there is an optimal solution which is consistent with our choice. So this is indeed a safe choice. So this gives us the following greedy algorithm. First, cover the leftmost point with a segment of length 2, which starts in this leftmost point. Second, we now don't need to cover any of the points which lie within this first segment. They are all already covered, so we can just remove them. And now we can solve the subproblem, which is the same problem with the remaining points which we did remove, which are not yet covered. And this is our greedy algorithm. We proved that the choice of the leftmost point and the starting segment of length 2 with the left end in this point is a safe choice. So this greedy algorithm is actually correct. And in the next video, we're going to implement it and analyze its running time and show that it is actually much faster than the naive algorithm we came up with in the previous video. Hi, In the previous video, we've came up with a greedy algorithm to solve the problem about covering points with segments, and that in turn gives us a greedy algorithm to solve the celebration party problem. In this video, we're going to implement this algorithm and analyze its running time to show that it is indeed much faster than the naive algorithm that we've came up with first. Let's start with this pseudocode. We assume that the points are given to us in the ascending order. So x1 is less than or equal to x2 and so on up to xn. And the function points cover sorted takes as input the points sorted by coordinate and outputs the list of segments which covers all these points, and all the segments are of length 2, and there is the minimum possible number of segments in the solution. We start with initializing the variable segments, which will contain the answer in the end, as an empty list. And we also initialize the variable left with 1, where left will be the index of the current leftmost point, the leftmost of all the remaining points which are still not covered. And so while left is less than or equal to n, it means that there are some uncovered points. In this case, we take the leftmost point with coordinate x left, and we create a segment with left end equal to x left, and the right end is equal to x left plus 2, because the length of this segment should be equal to 2. And we append this new segment to the solution. Then we see that the leftmost point is now covered, so we need to move left one position to the right, so we increase left by 1. And also we need to check maybe some other points, some next points are also covered by the same segment. So all the points to the right from the leftmost point we've just covered are to the right from the left end of this new segment. If they're also to the left from the right end of this segment, then they're covered. So while left is less than or equal to n, and the coordinate of the point is less than or equal to r, it means that this point x left is actually covered, and so we need to increase variable left by 1 again. So we move this left by 1 and by 1 until we find the point which is not covered, or until we go to the end of the array of points. And then we repeat this external while loop. If there is some uncovered point left, we create one more segment and so on. So when this external while loop finishes, all the points are covered by segments. All those segments are in the list segments, which is the solution, and we just return this list of segments as our solution. This is the implementation of the greedy algorithm we've came up with in the previous video. Now let's analyze it. The lemma states that the running time of this algorithm is linear. Indeed, the variable left changes from 1 to n. As soon as it becomes more than n, our algorithm stops. So although there is this external while loop and also an internal while loop with the same variable left, you could think that this leads to n squared running time, but actually variable left just increases at each step, and so it is increased at most n times. And for each value of variable left, we append at most one new segment to the solution. So everything we do is just we increase the variable left and we add segments. So we increase the value left at most n times, and for each of the values from 1 to n, we append at most one new segment to the solution. So all in all, we do at most 2n actions, and that is big O of n. So overall, the running time of our algorithm is linear. Now let's compute the total running time. Remember that when we implemented points cover sorted, we assumed that the points are given to us in the sorted order. So points cover sorted itself works in linear time, but we also need to sort the points before calling this points cover sorted function. And soon you will learn in the next module to sort in time big O of n log n. And then the total running time, if you're given points in unsorted order, will be sort plus points cover sorted is n log n plus linear time. Linear time is less than n log n, so the total running time will be n log n. And so now we see that the straightforward solution from the first video of this lecture is omega of 2 to the power of n. It's at least exponential, and this is very long, even for n equal to 50. Even just 50 children is too much to wait for a computation on your laptop. And sort plus greedy is just big O of n log n, so it will be fast even for n equal to 10 million. Probably you won't have 10 million children at any celebration party, but even if you have, your laptop will compute the solution for this celebration party in under a second, probably. So this is a huge improvement. So in conclusion, straightforward solution is exponential. And to improve it, it was important to first reformulate problem in mathematical terms, and we switched the problem from grouping children to covering points with segments. Then we came up to cover the leftmost point with the segment with the left end coinciding with this leftmost point, and prove that this is a safe choice. And our final solution is sort all the points in time n log n, and then launch a greedy algorithm in linear time. And in the next lecture, we're going to consider the problem of a burglar, how to maximize the loot that he can put into his knapsack before running. In this lecture, we're going to solve the burglar's problem of maximizing loot. Imagine that a burglar has broken into a house of a merchant of different spices, and he wants to take as much value with him as he can, but he only has a small knapsack
Hello, I'm Keith Devlin. Welcome to this online course on mathematical thinking. The goal of the course is to help you develop a valuable mental ability, a powerful way of thinking that people have developed over 3,000 years. What I want to do today is get you ready for the course and tell you a little bit about the way the course will work. I'm doing this because for most of you, this will be a very different perspective on what mathematics is. Apart from the final 2 lectures, there's very little mathematical content in the course, and you won't learn any new mathematical procedures. But mathematical thinking is essential if you want to make the transition from high school math to university level mathematics. The quickest way to learn what mathematical thinking is to take a course like this. So, by the time we're finished, you should know what it is. But for now, let me give you an analogy. If we compare mathematics with the automotive world, school math corresponds to learning to drive. In the automotive equivalent to college mathematics, in contrast, you learn how a car works, how to maintain and repair it, and, if you pursue the subject far enough, how to design and build your own car. The only prerequisite for the course is completion or pending completion of high school mathematics. That means many people could take the course and find it valuable. In particular, a key feature of mathematical thinking is thinking outside the box. In contrast, the key to success in high school math was to learn to think inside the box. It's because thinking outside the box is such a valuable ability in today's world that this course could be valuable to many people. But my primary student is someone in their final year of high school or their first year at college or university who's thinking of majoring in mathematics or a math-dependent subject. If that's you, then you'll probably find the transition from high school mathematics to college level, pure abstract mathematics difficult. I certainly did, and so did most mathematicians I know. Not because the mathematics gets harder. Once you've successfully made the transition, I think you'll agree that college math is in many ways easier. What causes the problem is the change in emphasis. At high school, the focus is primarily on mastering procedures to solve various kinds of problems. That gives the subject very much the flavour of a cookbook, full of mathematical recipes, thinking inside boxes. At university, the focus is on learning to think a different way, to think like a mathematician, thinking outside the box. That's not true of all college math courses. Those designed for science and engineering students are often very much in the same vein as the courses you had in high school. It's the courses that form the bulk of the mathematics major that are different. But some of those courses are usually required for more advanced work in science and engineering. So if you are a student in those disciplines, you may also find yourself faced with this different kind of mathematics. If you did well at math in school, you probably got good at recognizing different kinds of problems. So you could apply different techniques you learned. At university, you have to learn how to approach a new problem, one that doesn't quite fit any template you're familiar with. It comes down to learning how to think about a problem in a certain way. The first key step is learn to stop looking for a formula to apply or a procedure to follow. Approaching a new problem by looking for a template, a worked example in a textbook or presented on YouTube, and then just changing the numbers often won't work. Sometimes it will. So all that work you did at high school won't go to waste, but it isn't enough for many of your college math courses. If you can't solve a problem by looking for a template to follow, or a formula to plug some numbers into, or a procedure to apply, what do you do? The answer is you think about the problem a certain way. Not the form of the problem. That's probably what you were taught to do at school, and it served you well there. Rather, you have to look at what the problem actually says. That sounds as though it ought to be easy, but most of us initially find it extremely hard and very frustrating. It doesn't come quickly or easily. You have to work at it. You're going to have to accept going a lot slower than you're used to. Most of the time, you won't feel as though you're making any progress. Your goal has to be understanding, not doing. You should definitely try all the exercises. They're there to aid your understanding. You should also work with others. Few of us can master this crucial shift in thinking on our own. That part's crucial. A lot of what we'll be doing is not so much focused on right and wrong, but on learning how to think about a problem. Yeah, sure, at the end of the day, solutions are right or wrong. But usually there are many different right answers, or different ways to the right answer, and many wrong ones. When you're learning how to think mathematically, it's how and why you got something right or wrong that's important. The only way to find that out, got something right or wrong that's important. When you're learning how to think mathematically, it's how and why you got something right or wrong that's important. When you're learning how to think mathematically, it's how and why you got something right or wrong that's important. Mathematically, it's how and why you got something right or wrong that's important. The only, it's how and why you got something right or wrong that's important. The only way to find that out, to find out how well you're doing, is for somebody else to look at your attempt and critique your work. It's not possible to automate the grading process. Maybe one day artificial intelligence will have advanced far enough for a course like this to be automated, though frankly I doubt it. But right now, you need feedback from other people. For a regular class here at Stanford, the professor and the graduate student TAs grade students' work and provide feedback. With an open online course like this, where there are many thousands of students, that's not possible. So we have to go about things a different way. I've designed the course so that the benefit comes primarily from doing the work and discussing it with other students. Getting it right is important in mathematics, but in a massively open online course, a MOOC like this, there's no way to guarantee that. Incidentally, not being sure if we are right until others have seen our work is very familiar to we mathematicians. Even very famous mathematicians have had the experience of thinking they've solved a problem and writing up their solution and sending it off for publication, only for an anonymous referee to find an error. In mathematics, there is such a thing as right and wrong, but deciding between them can be very difficult. So even the professionals have to live with never being sure whether they're right or not. Part of this introductory session is a reading assignment. It gives you a bit of the history that should explain why today's mathematics students need a course such as this. In Lecture 1, there'll be a short quiz on the reading. Let me say a few words about the quizzes. If you were in one of my regular physical classes, I'd talk with you to find out if you had understood the material sufficiently to progress. But with a massively open online course, a MOOC, that's not possible. You have to monitor yourself. The quizzes are one way to help you do that. I'll say a little bit more about the quizzes later. But before you start Lecture 1, please read a file called Background Reading. It's just over 6 pages long. It's a PDF file, so you can download it and read it offline. I'm going to start off with a question.